This is the street lamp and shadow problem. It's well known in calculus, and most calculus students see it. So let's take a look at it. What we have is this. There's a street light mounted at the top of a 25-foot pole. We'll draw a picture here in a minute. Well, why not just draw it right now? All right, so I'm going to draw this situation. So let's just draw the skeleton of it here. All right, so here is a 25-foot pole. Now, I'm going to label that with a constant because the height of that pole is not changing. And here's the street light. Now, what happens here? We've got a 6-foot man, a 6-foot tall man walks away from the pole. All right, so there's a 6-foot man walking away from the pole. So maybe this is the man here. All right, here's the man here. And he's walking away from the pole at what? What do we know here? He walks away from the pole at 4 feet per second. Oh, now look at this, right? Rate. What do we think? We think derivative. And it's respect to time, right? You have a fraction here. The top is in feet, the bottom is in time. So this is going to be with respect to time that we're going to differentiate. Rate, derivative, with respect to time. So he's walking away at 4 feet per second. Now, what are we doing here? It says here, how fast is the tip of the shadow moving when he's 30 feet away from the pole? So this light here, this light right here is creating a shadow when it hits this fellow and comes down here. Let's draw that. All right, so the light comes down here and casts the shadow. So here is the length of the shadow right here. And what we want to know is, as this fellow walks away at 4 feet per second, how fast is this shadow length changing? You can see, what if we did this here? I'll do this in dotted lines. If the man is over here, the shadow is going to be much longer. So as time changes, the length of the shadow changes. And what we want to know is, how fast is that length changing when this fellow is right at 30 feet away from the pole? Well, we've got our picture. Now what we need to do is try to get an equation here, all right? So let's try to get an equation. Now, sometimes you can get equations just by formulas if it's a geometric situation, but this one we're going to have to work a little bit. Now, what I can see here is I've got similar triangles. Do you see two triangles in here? I'll draw this again without all that business in there. So there's two triangles here. There's this triangle, the big one, and the small one, right? And those are similar. Now I'm trying to get an equation that relates two things. I want the equation to relate this. I want it to relate the distance this fellow is from the base of the pole, and I also want to relate that to the length of to the tip of his shadow. Right? So I want to relate this distance here to the entire distance because that takes it out to the tip of the shadow. So I'm going to let this distance in here, right here. I'm going to let that be x. And then I'm going to let this entire distance here be y. And this is 25. And this one, now I know what that one is, right? That's 6. That's another constant. So by similar triangles, here's what I've got. I've got that 25 is to y, right? This vertical side is to the long base, right? The vertical side is to the long base. So let me write that. 25 is to y as what? The short vertical is to the short side. Now, I didn't label that x. This is x over here. So what am I going to write here? This is going to be, this distance here is the entire distance y minus this distance here. So I'm going to write it like this. This is going to be y minus x. No, it's not. It's going to be 6 over y minus x. Let's just run through it again. It's going to be the long base, or the long side to the long base, 25 is to y, as the short side is to the short base. Now the short side is the 6, and the base, because of my lettering here, is going to be the entire base minus what I've already used up. So I get y minus x. So let's do our cross multiplication here to multiply this out and get rid of those fractions. So we will get 25 times the y minus x equals the 6 times the y. This will give us 25y minus 25x equals 6y. I think I'll subtract this 25y, so I'll get negative 25x equals 6y minus 25y. I'll do it up here on the right now. So I get negative 25x equals negative 19y. Now, I could solve this for x or y. So how do I know which one to solve for? Do I solve for x or do I solve for y? Well, look back to the problem. That'll help us choose. Down here at the bottom, it says, how fast is the tip of his shadow? Well, the shadow comes out here at the end of this y right here. So I'm going to solve this for y. So I'm going to get y. I'm going to get y is equal to negative 25x over negative 19, or y is equal to 25 over 19x. There's our equation. Now I've got the equation. All I'm going to do now is differentiate. But I'm going to differentiate with respect to time, right? Because these are functions of time. So I'm going to get this. I'm going to get dy dt is equal to, now differentiate this with respect to time. Now this is a constant, so I'll just carry that along. So I'll get 25 over 19 and then dx dt, right? Remember, these are functions of time, so you don't get just 25 over 19. You got to take the derivative of the outside times the derivative of the inside. Now, let's substitute. So now I know that dx dt equals, what do we say up here at the top? That's increasing at 4 feet per second. So I'm going to write this as 25 over 19 times 4 feet per second. So this will give us now that dy dt is equal to, all right, what do we have here? Multiply 25 times 4 is 100 over 19, 100 over 19 feet per second. Now notice something interesting in here. Back over here, I'm going to go all the way back to the end of the problem. It says this: how fast is the tip of the shadow moving when this fellow is 30 feet away from the pole? Well, 30 feet, nowhere in our calculation did we have to use that. So this rate does not depend on that 30 feet or any other length for that matter. This rate of change is independent of where this fellow is from the pole. So no matter, I'll go up to the picture here, no matter where this fellow is, how fast is the tip of the shadow changing? How fast is that tip of the shadow moving? 100 over 19 feet per second. So here's my interpretation for this. I'm going to say that in the next second, right, everything's in terms of second, so in the next second, we expect the tip of the man's shadow to be increasing. Now we'll talk about why it's increasing, and not just changing, but increasing at the rate of, let's say about 5.26 feet per second. So two things. Why is it increasing? Well, look at the derivative. The derivative, dy dt, is equal to 100 over 19 feet per second. Now this number here is positive, right? And if the derivative is positive, that means the function itself, y, is increasing. All right, so I know that the tip of the shadow is increasing. Now, how fast is it increasing? Well, if I'm given any particular time, at any particular shadow, if we go one more second, right, one more second, this shadow is going to get how much longer than it was? about 5.26 feet. All right, and then you go another second. So another second, it's going to grow by even more. It's going to grow by another 5.26 feet.